Hello everyone, welcome back to the channel. In this video, we are going to discuss a GATE 2025 linear algebra problem and its complete solution. After that, we will see the core concepts involved behind the above problem. And finally, we will solve a few practice problems plus some problems for you to try yourself. So, let's begin. So, the problem is let x1, x2, x3, x4 and x5 be a system of orthonormal vectors in R10. Okay, which means these 5 vectors are orthonormal and each belongs to R10. Consider the matrix A, which is x1 x1 transpose plus x2 x2 transpose plus x5 xi transpose. Which of the following statement is correct? Singular values of A are also its eigenvalues. Singular values of A are either 0 or 1. Determinant of A is 1 and A is invertible. Okay. Now moving on to the solution. So what we have is given x1, x2, x3, x4, x5. These are orthonormal vectors in R10. Okay, these are orthonormal, which means that xi transpose xj is equal to 1 if I is equal to j, and it is equal to 0 if I is not equal to j for all I and j in this range from 1 to 5. Okay, this is the property of orthonormal vectors. And we have A is equal to inner product of x1, sorry, outer product of x1 plus outer product of x2 plus outer product of x5. Okay, now option 1 is singular values of A are also its eigenvalue. We need to find that whether the singular value of A is equal to its eigenvalue or not. Okay, so here we have A, which can be written as this summation I is equal to 1 to 5 xi into xi transpose, that is outer product of xi with xi. Okay, now we have to find singular values of A are also its eigenvalues. So singular values of A are, let's say sigma is singular value of A is nothing but positive non-negative root of eigenvalue of A transpose A. Okay, so what we have is, we know singular values of A are the non-negative square roots of eigenvalues of A transpose A, which means first we need to find the eigenvalue of A transpose A and then we take the non-negative square root and we get the singular value of A. Which means for finding the singular value of A, we need to find A transpose, then we need to find A transpose A, then we need to find the eigenvalue of A transpose A, and taking the square root, non-negative square root, we get the singular value of A. Okay, so what we have is, we have A can be written as this matrix, this is given. Now we need to find A transpose and A transpose A, okay, for finding the singular value of A. Okay, so let's moving on to the A transpose. Let's say what is A transpose is. So A transpose is, this is A into transpose. Okay, and we know A plus B transpose is nothing but A transpose plus B transpose. Okay, so applying this to this transpose, what we get is, this is nothing but first term transpose plus second term transpose plus fifth term transpose. Okay, which is equal to x1 transpose ka transpose, x2 transpose whole transpose plus x5 into x5 transpose ka transpose. Okay, and but we know that A into B transpose is nothing but B transpose A transpose. Okay, then xi into xi transpose is equal to xi transpose ka transpose. Okay, this is equal to xi transpose into xi transpose, but this is nothing but xi only, so this is equal to xi transpose. Okay, xi transpose. If we apply this to this, what we get is, this is nothing but x1 transpose only, this is x2 transpose, this is x5 into x5 transpose. This equation we get, this is nothing but just A. Okay, what we have given, so what we get is A transpose is equal to A. Okay, now we have A, we know A which is given, we have A transpose, just we found, which is equal to A. Now we need to find the A transpose A. Okay, so A transpose A is, we know that this is A transpose A. Okay, but we know that A transpose is given as A. Okay, So if we open this transpose, then we get this individual term transpose, okay, into A. Okay, then if we solve this, we get nothing because this is just equal to A. Okay, so A into A. So if we open this term, so what we get is x1 transpose into x1 transpose. So that is we'll get is x1 transpose x1 into x1 transpose, x1 transpose x1 transpose. If we multiply this x1 transpose with x2 transpose, then what we get is x1 transpose x2. Okay, this term is equal to 0 because why? Because x1 and x2 are orthonormal to each other. Similarly, multiplying this term with x3 transpose, x4 transpose, x5 transpose vanishes. Why? Because x1 is orthogonal. x1 is orthonormal vectors to x3, x2, x3, x4, x5. Okay, so only this term will remain. Similarly, for x2, and this product term will remain, the other product term will become 0, and similarly for x5. Okay, so finally what we get is x1 transpose x1 into x1 transpose, x2 transpose x2 into x2 transpose, plus x5 transpose x5 into x5 transpose. Okay, but here one thing we have to notice is x1 transpose x1, this is equal to 1. Okay, why? Because x1 is orthonormal. Okay, x1 is orthonormal, and we know that the norm of orthonormal vector is equal to 1. Okay, Euclidean norm is equal to 1, therefore this is 1. Similarly, this is 1 and this is 1. So what we get is, if this is 1, then x1 into x1 transpose, x2 into x2 transpose, similarly x5 into x5 transpose, this will become 1. This is nothing but equal to A only. Okay, then what we get is A transpose A is equal to A. Okay, what we get, A transpose A is equal to A. But we have found that A transpose is equal to A transpose is equal to A. If we put this A transpose is equal to A, this is nothing but A square is equal to A square is equal to A. This, hence A is an idempotent matrix, because this is the property of idempotent matrix. A square is equal to A. What we found. Now we know that. Now we need to find the eigenvalues. Okay, eigenvalues of A and singular value of A. Okay, so we know that using the eigenvalue equation, which is Ax is equal to lambda x, we can replace A with eigenvalue lambda in any polynomial of A. Okay, in any polynomial we can replace A with lambda. If we replace A with lambda, then what we get is lambda square is equal to lambda. Okay, where lambda is an eigenvalue of A. What we have is, we can replace A with its eigenvalue lambda in any polynomial of A. Hence what we get is a lambda square is equal to lambda, and taking lambda this side, lambda square minus lambda is equal to 0. Lambda into lambda minus 1 is equal to 0, and we get lambda is equal to 0, 1. This is the eigenvalue. This is the eigenvalue of A. Okay, what we get is the eigenvalue of A is either 0 or 1. Okay, now we know that the singular value of A, okay, singular value of A is nothing but the positive non-negative square root of A transpose A. Okay, this we have already seen, that is the singular value of A is non-negative square root of eigenvalue of A transpose A. Okay, but we know that A transpose A is nothing but A square. Okay, then it will become eigenvalue of A square. But we have already shown that A square is equal to A, and hence this will become the square root of eigenvalue of A, which is lambda. Eigenvalue of lambda. Okay, sorry. So let's start with fresh. We know that the singular value of A is nothing but square root of non-negative square root of eigenvalue of A transpose A. Okay, so but we know that A transpose A is equal to A square. Okay, so it will become eigenvalue of A square. Okay, if we know that the eigenvalue of A is lambda, then eigenvalue of A square is nothing but lambda square. Okay, then if we put this, if we put eigenvalue of A square as lambda square, and then we get the positive square root is nothing but lambda, which is nothing but 0 or 1. Hence what we get is, we get the singular value of A, which is nothing but the eigenvalue of A, which is 0 or 1. Hence what first statement is, it is singular value of A also its eigenvalues. This is correct. because the singular value of A is equal to eigenvalues of A. Correct only. Second is singular values of A are either 0 or 1. Okay, yes, singular value of A are either 0 or 1. This is B is also correct. Third is determinant of A is 1. Determinant of A, here we get the eigenvalues of A are 0 or 1. Okay, since the determinant of A is the product of eigenvalue. Okay, since the eigenvalue is one of the eigenvalue is 0, hence product is 0. So determinant will be 0. Determinant of A is 1. This is wrong. A is invertible. We have the eigenvalues of A are 0 or 1. Since the eigenvalue is 0, which means determinant is 0. Determinant 0, and hence in the matrix A is not invertible. Okay, that matrix A is not. This is also wrong. So what we have is B is correct. C is no, because determinant of A is 0. C is wrong, and D is also wrong because one of the eigenvalue is 0, determinant is 0, and hence A is not invertible. A is not invertible. Now coming to the core concepts that are involved behind the above problem. First one is the singular values of A are the non-negative square roots of eigenvalues of A transpose A, which means the singular value of A is nothing but non-negative square root of eigenvalue of A transpose A. Okay. Second one is if A square is equal to A, then A we call as an idempotent matrix. And one property of idempotent matrix is the eigenvalues of A are either 0 or 1. Okay, this we can see directly by putting lambda square is equal to lambda, then we get lambda is equal to 0 or 1. Okay, this is fine. Okay, now coming to some practice problems. So first one is let x comma y be orthonormal vectors in Rn. Okay, x comma y, these two are orthonormal vectors, both belongs to Rn, and we define matrix A such that x into y transpose plus y into x transpose. We need to find which of the following statements are correct. Okay, first one is eigenvalues of A are either 1, minus 1 or 0. A has eigenvector x plus y for eigenvalue 1 and x minus y for eigenvalue minus 1. C is all eigenvalues are positive, and D is determinant of A is always non-zero. Okay, and if we solve, we get is the options A and B are correct. Okay, we have some hint for that, which is okay. Let's start with option number B. And now we need to check whether x plus y and x minus y are eigenvectors of A or not. Okay, so for finding whether x plus y and x minus y are eigenvector or not, if we can prove that A into x plus y is equal to some constant times of x plus y, then x plus y is an eigenvector of A. Okay, similarly, if we can prove A into x minus y is equal to some constant time into x minus y, okay, then x minus y is an eigenvector of A. Okay, corresponding to eigenvalue lambda. By using this, what we can get is lambda is equal to 1 and lambda is equal to minus 1. These two are eigenvalues of A, and yes, x plus y and x minus y are eigenvectors of A. Okay, by using this, we get these two eigenvalues. And second hint is if we take z which is perpendicular, which is orthogonal to both x and y, then what we get is if we solve this equation xy transpose plus y transpose x, what is A is plus if we solve this, az is equal to this, where z is orthonormal to this and this, orthogonal to this and this, then we'll get 0, which means we get an eigenvalue 0 corresponding to z. Okay, and how many z can exist? There can be n minus 2 z that can exist. Okay, which means eigenvalue 0 has a multiplicity of n minus 2. Okay, using these hints, you will able to solve the question, and the correct option are A and B. So the problem number 2 is let u comma v be two orthonormal vectors in Rn. Okay, u comma v are orthonormal vectors in Rn, and we define A such that u into u transpose plus v into v transpose. Okay, we need to find which of the following statements are correct. First is u comma v are eigenvectors of A. Okay, second is eigenvalues of A are either 1 or 0. Third is A is positive semi-definite, and fourth is A is idempotent matrix. Okay, so what we have is we have given A is equal to this, and first we need to find u comma v are eigenvectors of A or not. We need to check whether A u is equal to lambda u or not, A v is equal to lambda v or not. If this is true, then we can say that u and v are eigenvectors, and we get the eigenvalue corresponding to these eigenvectors. Okay, this one is correct, and then using this we can get the eigenvalues. If we solve this, and then we get, yes, u and v are eigenvectors, and we get eigenvalue is equal to 1 in that case. If we take some z, if we take z which is orthogonal to u, and z which is orthogonal to v, okay, then we get az is equal to 0, and hence lambda is equal to 0 is also an eigenvalue of A, okay, with multiplicity of n minus 2. Okay, so we get, yes, these are eigenvalues. This is also correct. A is positive determinant. For proving A is PSD or not, we need to prove that Z transpose AZ is always greater than or equal to 0 for all Z not equal to 0. Okay, this we need to show. Yeah, if in this if you solve this, one property you will need, that Z transpose U is equal to U transpose Z, because this is inner product. Okay, inner product of Z with U is equal to inner product of U with Z. Okay, then we can easily solve. Okay, this is always greater than 0, greater than or equal to 0, and hence A is positive semi-definite. And for proving A is idempotent or not, we need to show that A square must be equal to A. Okay, so if we need to prove A square is equal to A is nothing but UU transpose plus VV transpose, multiplying with A only, UU transpose plus VV transpose. This will become A square, and we found that A square is equal to A only. If we solve this is also correct, and hence all the options are correct. All are correct. Okay, thank you. If you have any doubts or queries, let me know in the comment section below. You can also join our Telegram channel for the discussion or to ask any doubts directly. And for more such content, don't forget to subscribe. Thank you.